Good afternoon. Thank you for participating. My name is Alan, as Daniel said, and I'm the president and principal developer of StructureSolver. What we try and do is create intuitive and adaptable structural geology software that's actually fun and easy to use for people, so that solving structural problems while you're interpreting seismic or geological cross sections becomes an enjoyable and a rapid and a very sort of intuitive process. So I'm going to give a brief outline of StructureSolver. What is it? A technical summary with some examples, and then if there is time, I'll show how we interact very closely with Petróleo. So StructureSolver is an interactive 2D structural analysis software. We find that most problems that people have, a good chunk of the problem can be solved by analyzing things in 2D if you choose appropriate cross-sections through your structures. So the sort of challenges, interpretation challenges that we are able to solve are correlation across faults, shape of faults, the displacement on faults, how structures, how bed shapes develop as folding and faulting develops, how tectonics and stratigraphy relate, what is the internal strain of reservoirs, so all sorts of things we can get at with our software. And we use three different tool sets. One is structural restoration, the other is structural kinematic forward modeling, and the third one is area depth analysis. We do all of this analysis directly on the seismic or other data, allowing users to extract maximum geological insight from their data. So I'll briefly go through the tools. The first tool that we have is structural restoration, and structural restoration in StructureSolver is very simple. We've got one-click restoration where, having interpreted horizons and faults without any further issues, you can just, with one click, do an immediate restoration where we restore a section across all the faults. So we show an example here from an outcrop photograph. And this we can use to quickly validate cross-fault correlations, to unravel structural and stratigraphic history, and reveal tectonically masked stratigraphic features. For more complex structures, such as salt, diapirs, etc., or imbricated thrust structures, we have what we call structural component restoration, where we can very easily break an interpreted section into components and then restore individual components and then move those around to develop an overall restored section. And we can also do a variety of transformations with that data as well, such as what we call transform to target, stretch, shear, etc. So lots of things we can do with individual structural components in order to solve problems. So I'll just give a very short video at regular speed of what we call one-click restoration of that cross-section across a fault in the Moab area of Utah. So we've interpreted horizons in one fault, and immediately we just click on the fault to restore it, and the horizon to restore it, and instantaneously we get a flattened and restored section. Now on this section, we can add now additional interpretation on the restored section. So here we're just adding another horizon marker, another horizon across the section, and then we'll do one below the reference horizon. So you can imagine this is seismic data. We might have seen some correlations which were obvious once the section was restored. So here we're interpreting across the whole array of faults, and then we will just transfer those restored horizons immediately back to the original section, which is a really valuable thing to be able to do when you're interpreting seismic data. So we just go in here and then send the curve back to the original section, and you can see immediately the restoration goes back and is sort of retro deform back to the original section and becomes part of your primary interpretation. Likewise, you can put something on your original primary interpretation. So we'll just put a square box here and send that through to the restoration. So the full transformation between the two sections is maintained at all points. So here you can see that moving into the restored section. So that just gives you an overview of the one-click restoration. The more complex structural component restoration is useful for sections like this. So now we're actually in StructureSolver. This is the live program running here. It's a Windows program. We've got a variety. We've got file, export, import, edit, display, interpret, structural components, restore and transform, transfer curves, structural modeling, advanced modeling, area depth graph, and our help. So the help is very comprehensive. So anything that we're doing, we've got very detailed description of exactly the science behind what we do. And the help is fully interactive. So at any point when you're interpreting or doing something, you can just click F1 and get the help for that particular function. So anyway, here we have a section from the Gulf of Mexico. We've got an allochthonous salt body here, which has come up from the original Mother Luan salt. And at the point when the salt welled up and became allochthonous, these mini basins formed on either side. So it's not possible to restore this just in one click because the different parts of the section are broken up by the fault. So what we can do instead is we can take from this interpretation, you'll see here we've got, these are all the interpretation points that we can just change at any point. So it's completely live, the faults and the horizons. But what we will do is just create a marker from the original section, from the original interpretation. So we're just going to go around and select pieces of the original interpretation, which will be automatically connected to each other. So I've just outlined that section there based upon the interpretation. Then under my structural component menu, I can just create and drag across here into the workspace. I can just create and drag that structural component, and that is now completely live and it's referenced back to the original section, but it can be operated on independently at this point. So suppose we wanted to see what this structural component would look like at the time this red horizon here was originally deposited on the seafloor. Then we can just say restore sectional. Actually, what I will do first is I will just add some additional points to the end of that, just to ensure that we get sufficient aperture in the restoration. So that was just a modification directly on that. So now we're going to restore that component. We'll restore for that reference to that horizon there. We'll use flexural slip. We'll restore below that horizon. Here we've got all of the parameters of the section length, the deformed horizon length, the sum of the heaves, the nominal stretch factor, etc. And so then we just put in a pinpoint, say down in the syncline here, and immediately drag down the extent of our restoration, and there is our restoration. So we've immediately restored that component, which originally came from over here. We've restored it using flexural slip, and we've reconstructed the shape, the top of the salt at the time that that bed was deposited. So we can do this multiple times with multiple components. There's about 1, 2, 3, 4 components here. And then we can arrange those in a series of panels showing the sequential restoration of this feature. So starting at the bottom here, we're seeing the original mother salt is gray behind everything. And then we start to get the first bit of sedimentation deposited on top. Mini basins start to form. The salt breaks through. Salt breaks through further. Many basins continue to form. The salt starts to expand, reaches the seafloor, starts to become further and get greater lateral extent, and then starts to flow out basinward. Wow. And then we get a little raft deposited on top of it. So this is the sort of thing that people always want to do, and they do it with PowerPoint and they do it with various other tools. But here we're able to create a very complex restoration of a complex section in very short time. And furthermore, the process, because we can send restorations, send new interpretations backwards and forwards from the restored and transformed components, we can modify our interpretation and gradually refine our interpretation based upon the results of the restoration. So it's a very interactive process. So tomorrow, in the talk tomorrow, I'll give another example. We'll go into this process in more detail. So now let's look at something in a thrust belt that's using what we call similar technology, but using what we call transform to target, where we can actually construct intermediate stages. So we're already, yeah, okay. So here we've got a ramp anticline, which has been broken through on the back limb with a breakthrough fault. So we've actually got two stages of deformation. We first want to make a component on the top lot here, break that out very easily like we showed before, and then we can slide this component with this interpretation. We can slide that back down that breakthrough fault to remove the last phase of faulting. So we're doing that with an inclined shear algorithm in this particular case. And so this is just choosing the parameters or validating the parameters. And then we get to select how the hanging wall and the footwall correspond to each other. So we can just move this. This is a very flexible and intuitive way of, so here now we've restored that breakthrough fault, and we've now got the underlying ramp anticline, and we can now create components out of components. So we can create a new component above the ramp anticline fault from this one. And the history of all this is maintained very accurately. And we can just drag that down here, do the same for the footwall, and then do a flexural slip restoration of this transformed hanging wall onto the footwall of the ramp anticline to achieve our final restoration. So again, putting a pin top and the bottom, sliding it back, and you'll see our final result. We're always using all of the data. So we're always seeing the data when we do this transformation. We're not working with cartoons. And so we've got a good restoration here with the exception of this slight swell, remnant swell in the Silurian shale here in the intervening area, which we can actually take out in other ways. But that's our final two-stage restoration achieved just in that time that you've been seeing. So again, very quick. So now let's move on to structural modeling. With structural modeling, we do kinematic modeling based on structural principles that relate fold shapes to fault geometries. So we can use the same faults that we have in our interpretation for either restoration or also for structural modeling. The structural modeling use fault bend fold theory with shear axes related to bends in the fault that the structure is developing across. And we can modify all, the models are fully interactive. So, and then we also do that modeling directly on the seismic data. So we can match the actual observed seismic with the model and thereby gain information, very detailed information about the structure and how it developed. We can also put on things like strain ellipses and so on and so forth. So this is just an example here of really rather poor data from China in this case, and showing just how much information you can actually get out of seismic data by modeling. So in this case, we've got sort of a basement up here. We've got some hints of a fault down here. We've got some onlaps above the basement high. We've got structures in the forelimb, structure or folds in the forelimb, folds in the backlimb. So we start out by interpreting a very simple fault, adding a datum. We make this a tri-shear fault propagation fault, and then we're adding structural surfaces, which are model kinematic model surfaces. So we can immediately throw across that fault or slip across that fault, and then interactively modify the tri-shear parameters, which is the tri-shear apical angle and the start of the propagation and the end of the propagation, until we've matched the overall shape of the basement in the forelimb position. Then we can start to add points in the backlimb, add points to the fault, and then the model will automatically be extended into the backlimb area, and we can modify the fault here until we've done a good match of the basement topography there. So now we've sort of downward predicted the fault, we've matched the basement, and now we're going to add some surfaces in the intervening growth sequence, and then change the displacement on those surfaces, the horizontal displacement, in order to match the structure. So here we have to have quite a large amount of initial displacement in order to create this unconformity here. So we're modifying both the hanging wall and the footwall positions of those surfaces, and then we're adding in additional surfaces and then changing their displacement interactively to match the observed trend of the structures. So here we've got an intermediate surface here that's fairly well modeling, but you'll see as we add another surface, we get an even better model. So we'll add one more surface closer to the upper datum, and we'll see in order to match that, we actually have to move that in quite a way to match the dip in the forelimb here and also the dip in the back limb, and we get an erosion on the top of the structure here. So now with very poor data, we've actually managed to sort of create the displacement history of that fault and also the trajectory of the fault at depth and some elements of how it propagates. So we can automatically color that and then animate that fault to see the structural development through time. So we're doing that with a fixed fault, and then we can go backwards with a fixed depositional surface just to see how it would react if we were to do it as a fixed depositional surface. So you can see with very poor data here how much there's actually a lot of information implicit in the geometries of the seismic horizons in terms of fault prediction and also growth history on that fault. So yeah, so here we can also model normal faults. Sorry. Yeah.
Can Pedro just ask a quick question?
Yeah, sure.
Can you introduce a stretch curve to do decompaction?
Yeah, in our modeling, we're not doing decompaction, mainly for speed, and it becomes a very intricate linked system when you do decompaction. We can do burial history, as we're showing here in this particular example, and then in our restoration, because we now have full particle tracking through all of the stages of our restoration, we'll be adding a decompaction model in the next release. Generally, we find though that both modeling and restoration results are actually relatively insensitive to compaction, because most compaction takes place in the upper, the upper part of the section, and by the time we're looking at structural development at greater depth, usually most of the compaction has taken place. So, and that's been found by a number of workers have found that. So, generally doing these things without, having the speed of doing them without decompaction is a good trade-off. But here we can see here in this particular case, here we're modeling a little normal fault, but with a period of uplift and erosion. And you'll see that you create actually interesting unconformities. And when you actually model something like this in real life and model these unconformities, you actually unravel the burial history of the structure. So just to show you a little bit more about the sensitivity of these, the modeling, here is a very well imaged, in this case, we're using a very well imaged structure from the Niger Delta. It's again, a fault propagation fault. There's a major fault with 2 back thrusts. There's a pre-growth section here. If we restore this, we'll see that all of this section below, actually this pinkish horizon here is pre-growth, and then all these purple horizons here are growth sections. So there's less and less structure. So these were being deposited as this structure was being developed. So we could explore the evolution of the structure through a series of restorations, but another way of exploring it is actually to do a structural forward model of it. So this again, this is the interpretation, but now we're going to actually look at a forward model. So here's the same structure, and the only thing that's interpreted now is the fault. But we've created a model, just like we showed you. We've created a model for that. So there's the model. If we turn on color fill, with that, we'll see that's, and you can see that these beds now actually match, these model beds match very well the shape and the position of the interpreted horizons. If we animate this, then you'll see the structure developing. That's the pre-growth. And then the fault starts to propagate. As the fault propagates, we get a forelimb and a back limb, and we get those series of growth horizons being deposited. So what did it take to do this modeling? Well, let's look at the different parameters involved. First of all, if we turn on the displacement vectors, you'll see the primary thing is how much displacement there was in each of these model surfaces. So if we take an individual model surface, we can move that around, and you'll see it will change, and it will also change things around it as well. So, but the most important thing, because we've got pre-growth here, is all of these beds here have got the same displacement up to here. So if we change the overall amount of growth, suppose we increase the pre-growth displacement, you'll see that we won't match either the growth horizons or the shape of the pre-growth horizons. So that's the first thing, matching the displacements. So the second thing is, let's turn on the shear axes, and you'll see that the deformation is controlled by shear on these shear surfaces coming from fault places, and also from the tri-shear zone at the tip of the fault. So I'll turn off the color fill just so you can see this a little clearer. So if we change the fault shape just by modifying, you'll see as we change the fault shape, the model will change. So the fault shape has to be pretty well constrained. If we change the start of the fault propagation, you'll see we develop a steeper forelimb. If we change the end of a propagation, we again will change the details of the structure in this area here. And likewise, if we change the shear angle, tri-shear apical angle, we will also diverge from the observed geometries. And then on the back limb, the structure on the back limb is very sensitive to the shear angles that the shear angle we use here. So we can also change that. See, if we make a steeper shear angle, we'll see the structure becomes much more contracted. If we make a shallower shear angle, we actually have to have a shear angle that actually matches these two back thrusts that we see here. So what I'm trying to show you here is that the observed geometries actually constrain the model parameters very, very closely. And when we do match, as well as this, we're getting a lot of information about the structure. So for instance, we can add strain ellipses to the structure. So here we can add a strain ellipse, and you can see that this back limb area here is actually experiencing quite a lot of contractional strain, up to 20% of strain. Around the forelimb area, again, large amounts of contraction. And we can add these strain ellipses and then watch them animate through the structure. Whereas the top of the structure, through here, for example, anywhere through the top of the structure, you have no strain. That top of the structure is being, so this is telling you something about what's happening to the reservoir. And when we animate this, we can actually see those strain ellipses being deformed automatically through the thing. So let me just hide the image off. Actually, let me add some more strain ellipses. So this is telling you something about what's happened to the actual rocks. So we animate that at this point. You'll see that those strain ellipses start out as circles, and then as the structure develops on both the back limb and the forelimb, they start to deform. So that's telling you how much deformation there is in the structure. So, but if we go back to the original section, you'll see that there was actually two back thrusts here. So we can go further here and actually model, we can actually model all of the faults together and then link them together. And that's pretty interesting. So in this case, we can actually put some back limb thrusts in here and then create individual models for each of those faults and then automatically link them. So there's a structure, a model that models the forelimb area. Here's a model that just models the vicinity around that fault. And here's one that models just in this area here. So we put all of those together. Then as long as they match where the hanging walls and footwall coincide, we can do an automatic animate link models that will give us the overall structural development with all of the faults active. So, and this is, as long as you've done a good job of the individual fault modeling, this is an automatic process. It doesn't always work because sometimes there's a lot of interference between faults, but if there's relatively little interference between fault blocks, then that's okay. So you can see that as this fault propagates, first this back limb fault activates, then it deactivates when it comes up onto this flat part of the fault, and then this second fault activates. So you see that again. I'll turn that. So this is giving you a very good understanding of exactly how this structure developed. And we can do these link models for a variety of, extensional models, contractional models, etc. So And we can also do them with where we put ages and we've got erosion and down cutting and so on. So this is an example from the Bohai Basin in China, where we've got a big extensional fault, a very low angle extensional fault, with these rather dramatic unconformities throughout the section here, right? And those unconformities have developed in response to a period of extension followed by a period of down dropping and then further extension. So we turn on the structural model for this fault. That's the structural model for it. And then if we show the burial history for it, so now we're getting a little burial history thing. And if we show animation for this, you'll see how we develop these unconformities. So all of these surfaces now are fully computational. And they're based again on the shape of the fault, the shear angles, and the displacements, and in this case, the burial history essentially. So you can see now we're dropping down and we're developing those unconformities and then finally building up the last bit of the section. So, but again, this is, we can look at this structure out here now, the outboard structure, and it's the more regular. It doesn't have nearly as many unconformities. It's got these ones here, this thinning here, and if we look at the burial history for this, which is automatically defined, and then we animate this one. Oh, sorry, still got that available. Animate this one. You'll see now it's the down dropping period, further extension, and then build up again. So this is all matched, created by matching the observed geometries and ages. So what we can do for this now is then again link these models. Sorry. Yeah, so now we've got two structural models, and you'll see of necessity this outboard fault must move on the inboard fault. So we do a linked model for this one. Takes a few seconds just, and there's some slight mismatches here. You'll see how the overall structure develops. So the inboard fault develops first. The outboard fault has not got any displacement on it at this point. It's just moving. Its incipient trace is moving on the inboard fault. It starts to develop some displacement. Eventually falls off the ramp in the inboard fault. The inboard fault starts to deactivate, and then the outboard fault starts to activate much more strongly. So you can see this is the sort of analysis of a complex structure like this that's very difficult to actually achieve simply by looking at the structure. The modeling, and then we can also do restorations on these, which I don't have time to show you, but they're also very insightful. So that's pretty much got through the restoration and modeling. What I haven't shown yet is how we use area depth analysis. Daniel, do you want me to do that quickly, or just stop at this point and ask for questions? Hello?
It's clear.
Yeah. So I can go very quickly through area depth analysis if you'd like at this point, because it's also a very useful and powerful tool that can be used in conjunction with. So what area depth strain analysis does, we take structures, interpreted structures, and then we measure the area of beds, pre-growth surfaces. We measure the area, either excess area or area deficit in the case of extended structures, and we measure those areas automatically, and we graph them versus depth. And it turns out that the slope of the area with depth gives you the true displacement on the structure, and the point at which the area goes to zero gives you the detachment depth. That's for a structure that detaches into bedding. We've also extended that extended that theory to manage faults that go and cross-cut the stratigraphy at depths. In that case, we can estimate the fault trajectory as well as the displacement on the fault. So this is a very powerful technique. It's not often used because there's just a lot of computation involved. But what we've done is we've sort of automated that. And then we can also, this takes a little more explanation, but by comparing actually restored bed lengths with true displacements from area depths, we can get estimates of how much internal deformation there is in beds, how much layer parallel strain there is, which is really powerful because we find most structures have layer parallel strain of 3 or 4 or 5%, either extensional or contractional. So let's just quickly look at an example of this. We go back to that Niger delta. Now we're going back to the interpretation. So we've got this faults, and we will use that interpretation now to get an estimate of where the detachment is and also what the displacement on these faults are. And we can compare that displacements with the displacements we get from our modeling. So to do this, we just create an area depth graph. We can select a color. I'll just do black, pen width, etc. We're going to use detachments solving parallel to the regional stratigraphy. And then we just start selecting horizons. And every time we select a horizon, that the area of that horizon above the regional level is automatically computed and plotted horizontally from this vertical line that goes down the center of the section. So each of these little squares here represents the area of one of these beds, taking the faults into account. So if we just display, so here you'll see that's the area of the blue, the light blue, the darker blue, the green. So you can see the areas are getting bigger and bigger as you get above the detachment up until the top pre-growth interval, pre-growth horizon, which is there. And then in the growth horizon, the areas get smaller and smaller and smaller because these beds have experienced less displacement and consequently less area, less fold has been developed. So the software automatically determines the breakover between the pre-growth and the growth. It projects down here, gives the detachment level, which we can see matches the observed fault very well. And then here we see the displacement vectors for each of these beds. So you can see all of the pre-growth has got the same displacement of about 775 meters. The actual bed length shortening, apparent bed length shortening is only about 193 meters. So if we flatten that bed out, we only get 193 meters of shortening, but there's actually 775. And the difference between those two is about 8% of layer parallel strain, which is identical to that strain we saw from the strain ellipses in the structural forward modeling. And then you can see, the displacement gradually decreasing through the growth. So this technique's independent of anything else, gives you the full displacement history on this fault. And it also gives you very good estimates of how much internal strain there is in the reservoirs, in the beds, which may be reservoirs, okay? So we can also do that. The same technique works with cross-cutting faults. So here we've got an example from Argentina where now we've got these beds have been interpreted in the upper section. We've got what appears to be a basement, a fault plane reflector down here. In this particular case, we chose this case because we could actually see what looked like a fault plane reflector, so we could validate in some extent. But now we're going to just use the data of this faulted fold up here in order to predict where the fault actually goes at depth and also the total displacement. So again, in this case, we just create an area depth curve. In this case, we'll use the fault trajectory method. We'll let the fault cross-cut the stratigraphy at depth. And then we'll start choosing our horizons again. Let me just change that color to red, for example. So what this has done now is automatically determined not just the displacement and the depth of the fault, but also the dip of the fault. So here it's saying that at this point, at this regional limit, that fault is dipping by that amount, and it's got that amount of displacement. Let me just extend the workspace a little bit. So we can see that off the edge there. So that's an estimate of the fault dip, displacement, and position at this regional limit here. We can change that regional limit, either regional limit at that footwall or the hanging wall side. And as we move that regional limit in, we'll start to actually trace the shape of the fault. So you can see the way that lower arrow and the dotted line actually start to trace. Now we've gone over the edge of the fault, but up till that point, we can estimate the entire fault trajectory. So again, this is a really powerful technique in both thrust and extensional regimes in order for figuring out where faults go with depth and independently figuring out how much displacement is on the fault. So I think that I better just stop at this point. I've got lots more examples I can go on for a lot more. Tomorrow, we'll give a more detailed basin scale examples from the Sichuan Basin showing both restoration and transformation of data. So with that, I'll stop and just come back to title slide here. This is my email here if you have any questions, or just directly, obviously, talk with Daniel and Sonia if you're interested in our software. Our software is used by a variety of companies, big companies, small companies, national oil companies, individual consultants. So we have this software deployed around the world. We've got a very tight and useful Petróleo link where you can go backwards and forwards between Petróleo and StructureSolver. If you look at our website, StructureSolver.com, you'll see an interactive video showing how to go backwards and forwards with Petróleo, which is extremely easy. So we have a plugin for Petróleo. You can just immediately put interpretation from Petróleo into StructureSolver, modify the interpretation, add to it, send it back to Petróleo, and go backwards and forwards. So with that, I'll stop and appreciate your interest and attention. Thank you.